Chapter 9, Power Series. Section 9.1, Approximating Functions with Polynomials. This section, we will look at what is the power series, Taylor polynomials, approximations with Taylor polynomials, remainder in a Taylor polynomial, estimating the remainder. What is a power series? The power series center at x equals a is of the form summation of the ck multiplied by x minus a to the power k, where k equals 1 to infinity, or c0 plus c1 x minus a plus c2 x minus a to the second, and keep going. For k equals n, the term is cn x minus a to the power n. For the power series centered at x equals 0, the infinite series is of the form summation of the ck times x to the power k starting from 0 to infinity, or c0 plus c1x plus c2x squared, and so forth. Note, x equals a is called a center of the polynomial, where the coefficients ck are constant. This type of the series is called a power series because it consists of the power of x minus a, or in the case that a equals 0, it's going to be the power of the x. The series is built up from the polynomials of increasing degrees, as we see the summation of ck x minus a to the power k from 0 to infinity. This form is the infinite series form, or we call the power series. On the right-hand side, in the expansion of form of it, we have c0 plus c1 x minus a plus c2 x minus a to the power second, and so forth. For the first term c0, or as c0 times x to the power 0, we call the 0-degree polynomial. Add another term as we add c1 x minus a raised to the power 1. This is the polynomial degree 1. Add another term with the degree 2. We obtain the second degree polynomial as c0 plus c1 x minus a plus c2 x minus a to the power second. If we expand until the nth power, the sum of c0, c1 x minus a, c2 x minus a to the second, up until cn x minus a to the power n is called the nth degree polynomial. Taylor polynomial centered at x equals a is of the form Pn at x equals fa plus f prime at a over 1 factorial times x minus a plus f double prime at a over 2 factorial times x minus a to the second up until the nth term, which is the nth derivative at a over n factorial times x minus a to the power n, or in the summation form as the Pnx equals summation of the ck times x minus a to the power k from 0 to n. The coefficient ck is of the form the k derivative of the function f at a divided by k factorial for k equals 1, 2, 3 up until n. Approximating with Taylor polynomials. The linear approximation, linear means the power 1, so the p1x is fa plus f prime a times x minus a. The quadratic approximation, quadratic means the degree 2, or the notation P2x is fa plus f prime at a times x minus a plus f double prime at a over 2 factorial times x minus a to the second power. Or we can say the P2x is the P1x plus the second derivative at a over 2 factorial times x minus a to the second. And same concept, the cubic approximation, cubic means the power 3. So the P3x is the sum of the fa, f prime a, x minus a, f double prime a over 2 factorial, x minus a squared, and the third derivative at a over 3 factorial over multiplied by x minus a to the power 3. Or we can rewrite the P3 as P2 plus the third derivative at a over 3 factorial times x minus a to the power 3. Examples. Given functions f of x equals square root of 1 plus x. Part A, find the linear and quadratic approximations for f of x centered at x equals 0. Part B, use these approximations to estimate square root of 1.1. Part C, compute an absolute error as absolute value of the difference of the approximation and the exact value. For part A, we're going to use the Taylor approximation to find the linear and quadratic approximation centered at x equals 0. So the Pn at x, or the Taylor polynomial centered at x equals 0, is f at 0 plus f prime at 0 over 1 factorial times x plus f double prime at 0 over 2 factorial times x to the second plus f triple prime at 0 over 3 factorial times x to the third up until the nth derivative at 0 over n factorial times x to the power n. For the linear approximation, the P1x equals f at 0 plus f prime at 0 multiplied by x, and the quadratic approximation P2 of x is f at 0 plus f prime at 0 times x plus f double prime at 0 divided by 2 factorial times x squared. So we're going to need the function at 0, the f prime at 0, and the f double prime at 0 for these two approximations. As f of x equals square root of 1 plus x, the function at 0 equals square root 1 or 1. The f prime of x is 1 over 2 square root of 1 plus x. So then the f prime at 0 equals 1 over 2. The second derivative, which is from the derivative of 1 half 1 plus x to the power negative 1 half, we get negative 1 over 4 times 1 plus x multiplied by negative 3 over 2, or negative 1 over 4 multiplied by 1 plus x to the power 3 halves. So then the second derivative at 0 is negative 1 over 4. And then we use these numbers to form the linear approximation and quadratic approximation. For the linear approximation, P1 equals f at 0, which is 1, plus the f prime at 0, which is 1 half, multiplied by x, and the quadratic approximation, or the P2x, which is from the P1x plus additional term, or the term with the second derivative at 0 over 2 factorial times x squared, which is 1 plus 1 over 2x minus 1 over 4 multiplied by 1 over 2 factorial times x squared. Therefore, we get the P2x equals 1 plus 1 over 2x minus 1 over 8 times x squared. After we get the first and the quadratic approximations, we are going to use them in part B to approximate the square root of 1.1. So in part B, square root of 1.1 as a function in the form of square root of 1 plus x. Therefore, the x that we are going to use is 0.1. Therefore, square root 1.1 approximately equal to using the P1x, which is the P1 at 0.1, or the value from 1 plus 0.1 divided by 2, then we get 1.05. And using the quadratic approximation P2x, which is from P1 at 0.1 plus additional term, which is negative 1 over 8 x squared, so we get 1.05 minus 1 over 8 multiplied by 0.1 squared, and we get 1.04875. Next, in part C, we are going to find the absolute error from using each approximation. From the linear approximation, the absolute error equals the absolute value of the approximation minus the exact. Approximation is 1.05 minus the exact, which is square root of 1.1. And then we get the value negative 0.001191115 for P2 or quadratic approximation. The absolute error is the absolute value of 1.04875 minus square root of 1.1, which gives us 0.00005888482.